Hey, welcome to the week number one, part five. So, this week, okay, we're ready. So, this lecture number three is talking about the whole, all the details written in chapter two, especially section 2.1 to 2. So, try to read out chapter two of the textbook. Okay. So in this lecture note, we're gonna learn what the electrons and holes are. So electrons and holes are, flowing the current. You're gonna hear this type of sentence. Electrons and holes are moving from here to there. And now in this electronic component, or maybe in this transistor, the electrons are moving away from the source side towards the drain side, and throughout the channel region, the electrons are, moving following the mechanism of drift instead of diffusion. So to understand what the electrons and holes are in electronic devices, we need to first come up with and build up our own understanding and fundamentals of what the electrons and holes are. Afterwards, to describe how high or how low each electron and hole has its own energy, we need a certain tool. Instead of using color to indicate this electron has very high energy, then you may imagine the red color to indicate this electron has very high energy. And that electron has a relatively small amount of energy, so let's use a blue colored one. But in this case, you can only use two different colors. In other words, you can only express two different energy levels. That's it. What if the third electron has a third different energy level? Then how can you express it using two colored pencils? No way. Okay. So in that sense, we need a certain new uh, tool to express the energy values of all the electrons and holes. But previously, I talked about how many silicon atoms are existed in a cubic or in a cubic centimeter. Do you remember the number? That was 5 times 10 to the 22 per cubic centimeter. And again here, each silicon atom has how many outest electrons? It has, let me see, here the silicon atomic density is 5 times 10 to the 22 per cubic centimeter and 4 electrons per silicon atom, right? Definitely 14 electrons are existed in a silicon atom, but only 4 outermost 4 electrons are available. For what? For making current flow in an electronic component. Okay, so 4 candidate electrons are available per each silicon atom, and per cubic centimeter, we have 5 times 10 to the 22 silicon atoms. So we can do simple math, and we end up with 4 times 5 times 10 to the 22. In other words, 2 times 10 to the 23 electrons per cubic centimeters are available for making current flow. Okay. Then can you use only two different colored pencil to express the energy level of 2 times 10 to the 23 electrons? That's impossible. So we need to come up with and build up a new tool to express the energy level of each electrons and hole out of 2 times 10 to the 23 per cubic centimeter. Okay? So in the very first lecture note, let's take a look at the electronic properties of silicon. So silicon, atomic number is 14, and it has a full outermost electrons. So this silicon is a semiconductor material. You may remember in terms of resistivity, conductivity, silicon has the conductivity or no, no, resistivity of silicon material is in the range of 10 to the minus 3 to plus 3 ohm centimeter. But pure silicon, I have told you, 10 to the plus 4 ohms. Okay. So this pure silicon has a relatively high electrical resistivity at room temperature or 300 Kelvin. However, it is still a semiconducting material. So let's do that. Let's do uh, understand why the silicon's resistivity is out of the range, general range for semiconducting material. Again, so we're gonna insert non-silicon atom into the silicon crystalline material, then we can tweak, control, modify. What? Modify the electronic properties, definitely conductivity or resistivity of silicon. So even though the pure silicon has a relatively high electrical resistivity at room temperature, there is no problem. It is okay because we're gonna put some non-silicon atoms, some impurities into the silicon material, then we can control and modify the semiconductor's electronic property. So what is the main actors for making current flow? For making current flow, well, many general people can guess. Silicon atom has a full outermost electrons, so that electrons would be used to make current flow. That's true. But for those of who uh, majoring in the semiconductor device physics, I'd like to ask you to come up with some other carriers to flow to current flow. That is Hall. Okay, so uh, electron is the thing that they are really existing within a silicon material, but hole means empty one, vacant one. So hole is not really existing particles. However, hole itself looks like a particle which is moving around within a silicon diamond structure, the silicon crystalline material. So we can say that there exists holes, but that's not the real one. That's a fake. Okay, but it is in some cases it is much easier to express and indicate the current is flowing by holes instead of electrons. So in that sense, we need to consider the empty site or vacancy as carriers for current flow. Okay, so people has developed and claimed that there exist two different types of mobile. Again, mobile, not non immobile, mobile charge carriers in silicon material. So what are those? Conduction electrons and holes. So conduction electrons, is it quite different from electrons? In some sense, yes, it is quite different from electrons. What is the main difference? Conduction electrons indicates the electrons can contribute to flow current. The electrons itself indicates you know 14 electrons in a silicon atom. But we're gonna use a full outermost of electrons to flow currents because they are running the most away from the center site of the silicon atom, so which is loosely bound to the positively charged particle within a silicon atom. The four outermost electrons will be used, and the electron is negatively charged. And once electrons are missed out and there is nothing, then we can say that this hole is now moving, and the direction of movement of the vacant site, quite opposite to the movement direction of the electrons, so that we can claim that this empty one holes are positively charged. Okay? So in summary, in silicon, there are two types of mobile charge carriers, which are conduction electrons or holes. They are oppositely charged. All right, let's take a look at the third bullet. The concentration in the unit of number per cubic centimeter of conduction electrons and holes in a silicon semiconductor can be controlled, modulated in several ways. What is the main way? Here, number one, as I told you, by adding by inserting special impurity atoms, namely dopants. Instead of silicon, different atom can be included in a silicon crystalline material. Then we can say that we have added special impurity atom. We have doped silicon material. For what purpose? To modulate the concentration of electrons and holes. Again, in pure silicon means, you know, only silicon, right? No other, atoms in this silicon. In pure silicon, by adding up non-silicon atom into pure silicon, okay, pure silicon, we can control number of diameter of electrons and holes. This is quite a magic. Just by simply adding non-silicon atom into the pure silicon crystalline material, diamond structured silicon material, we can control the total number of electrons and holes. Why is it important? The number of electrons and holes will be the main key knob how much current can be flown in a silicon material. Think about the digital computer. People are saying that digital computer is working with two different digit numbers, 1 or 0. How to express 1 or 0 in transistor or in diode or any type of electronic component? You may guess that what if the current is flowing, in other words, the diode is or transistor is on, then we can say that it is now expressing 1. Once the transistor is turned off, and since it is not flowing current, we can say that this is indicating the number of 0. So once transistor is turned on and off, we can express digital number 1 or 0. What is main actor for flowing current? Again, that is conduction electrons. Where does conduction electron come from? Four outermost electron of silicon atom. Okay? Because they are loosely, weakly bound to the positively charged particles of silicon atom. Therefore, by adding non-silicon atom, we can control the total number of electrons and holes, resulting in the amount of current flow in a certain electronic component, such as diode, transistor, in digital computer. Okay, and this is kind of magic, right? By simply adding very small, tiny amount of impurity atoms or dopant atoms into the silicon atom, we can control the total number of electrons and holes. Okay, so we're gonna study some details, the impact and effects of adding special impurity atoms on the concentration of conduction electrons and holes in a silicon material. All right, and the other way to control the concentration of electrons and holes can be found by applying an electric field. So electric field, the concept of electric field is like this. For a given voltage difference, within a voltage difference, the area having a different amount of voltage level, that area is exposed with an electric field. So within an electric field, not gravitational field, the charged particle, okay, I'm not talking about neutral charge, neutral one. Once a particle is charged negatively or positively in an electric field, those charged particle will be forced, will give, will receive a certain amount of force out of the electric field. Then, what is the carriers being charged in silicon? Electrons and holes, right? So those are two different type of mobile charged carriers, electrons and holes, will be split, will be moved, will be away, will be conglomerated, will be, you know, will be get in a certain hotspot because of what? Because of applying an electric field across the electronic component. So in transistor, we're gonna apply a certain amount of voltage to a certain region, say gate, source, drain. Those are the three terminal names of transistor. So gate voltage is higher than the drain voltage, and for given biasing condition, which means electric field is now modified for what? For modify for modulating the total concentration of electrons in holes. So that is the second way of tweaking the concentration of electrons in holes. Right. The next one is a very simple one. By changing the temperature, we can have more electrons. We can induce more electrons and holes out of the silicon atoms. The lower the temperature is, the smaller the total number of electrons and holes are from silicon atoms, or from the crystalline silicon materials. The last one is by irradiation. So irradiation means that the heavy ion beam, alpha particle, beta particle coming from the space will modulate the total number of electrons and holes in crystalline silicon materials. So as I told you, the four outermost electron is relatively loosely bound to the center part of the silicon atom. But once very high energy beam has hit the silicon atoms, then the very first two electrons which are sitting on the 1s orbit, maybe not, but maybe most likely to be freed out. Then the total number of free electrons would be modulated. Okay? So the electronic system for the aerospace application by radiation, the concentration of electrons and holes are modulated, resulting in a some ill operation. These are computers for aerospace applications. Maybe in this lecture, I won't talk about too much about aerospace application, since these class and lectures are designed to have all the students to simply and easily understand how the DRAM, NAND flash memories, CPU, cache memories are working. So for that purpose, I'm going to provide some basics and fundamentals of solid state physics. Okay? So after midterm, we're gonna study PN junction diode and Schottky diode, metal semiconductor junction diode. And next semester, I'm going to teach some fundamentals and basics of transistors and MOS system, metal oxide semiconductor system. So most capacitor, most FET, those are the key, core part of the DRAM bit cell, access transistor. The transistor having an MOS system, and NAND flash memory MOS system is a basic part of it, and the cache memory or SRAM, more than 75% of chip area of Intel and AMD CPU is filled up with a SRAM array. So SRAM has been consisted with 6 or 8 transistors for a single data bit cell. So MOS capacitor, MOS FET field effect transistor, those are the basic fundamental electronic components in memory and system IC devices and chips. Okay, so in this lecture again, I'm going to teach you some very fundamentals and introduction of solid state physics to understand how the PN junction diodes and MS diode or Schottky diodes are working. Afterwards, in this upcoming fall semester, I'm going to teach you some fundamentals of MOS capacitor and MOS FET to explain how the semiconductor memory is working. Right. Now let's move on to the bond model or bonding model of electrons and holes. Previously, when I'm teaching you how the silicon atoms are placed in a unit cell, you may remember that for a given silicon atom, on top of it, silicon atom is connected and bonded, and below it, you may imagine three silicon atoms below this silicon atom, and it has been bonded with a covalent bonding. And those silicon atoms are placed on corner of triangular. And if I'm connecting the dotted line to the top silicon atom, then we're gonna have a tetragonal structure. So this is 3D. This shows the three-dimensional view how the silicon atoms are connected with the full neighboring silicon atoms. But it is hard to describe and hard to draw it every time. So people love to use a two-dimensional representation. So this is a silicon atom at the center, which is corresponding to this guy. Okay? And on top of it, another silicon, and below it, there are three different silicon atoms. Okay, all right. And as I told you, a single silicon atom has four outermost electrons, and this silicon has also four outermost electrons. Here, in between two silicon atoms, those two electrons are shared to each other, and they're gonna build up the covalent bonding. Okay, so this two-dimensional representation has been named as bonding model or bond model of silicon. Now, take a look at the image on the bottom side. When an electron, say, suppose that this electron, when an electron breaks this covalent bonding and is now freed out, becomes which means this electron has become the conduction electron. Now this electron is away from the silicon atom, okay? But still, this electron is limited and alive within a crystalline silicon material. Okay? When this electron becomes conduction electron, take a look at here. What else has been left behind? Hole, right? Nothing. Hole means nothing. Vacant one. Vacancy. So this hole has been left behind. Okay? At 0 Kelvin, so all the electrons are frozen out, then electrons would be sit down here. But once temperature is increased up to 300 Kelvin or room temperature, then this electron becomes a conduction electron. Hole is created. I said created, generated. Hole was not existed at all previously at 0 Kelvin, but at room temperature, one of the four outermost electron has become conduction electron. As a result, a hole is created. So this conduction electron, and this newly created electron hole, are created in pairs. So I said electrons, this electronic pen is not working properly. Electrons and holes are created in pairs. Okay, so E, H, P. So EHP. So EHP has been created. Okay, So in a pure silicon diamond structure that is constant again, face center cubic diamond structure, simple cubic, you all remember these things, right? So at room temperature, electron hole pairs are created, which means once a single free electron is created, we always have one more hole. Okay? So electron holes are created together in pairs. Okay? So people are saying that EHP has been created. Okay? So in this bonding model, this process indicates how the EHP are created, electron holes are created. Okay. Uh, so here I would like to tell you some more the number, how many conduction electrons are created at room temperature. So take a look at this figure. X-axis indicates the temperature in the unit of Kelvin. So here 300 Kelvin. In case of silicon, let's move on here. Yes, there we go. 10 to the 10. So here y-axis indicates n sub I in the unit of number per cubic centimeter. So I indicates intrinsic. Intrinsic means pure. Okay. So solely silicon atoms are used to build up the crystalline silicon material. You can say that this is pure silicon or intrinsic silicon. So in this intrinsic silicon material, how many electrons, conduction electrons or free electrons are available at room temperature? Well, definitely at 0 Kelvin, there is no free electrons because all electrons are frozen out and has participated in bonding, uh, participated in making covalent bonds in between two silicon atoms. However, at room temperature, a certain amount of thermal energy, external thermal energy has been included. So pure silicon has been exposed to a certain amount of thermal energy so that a certain amount of electrons, conduction electrons are created so that we need to understand how many conduction electrons are created. So the answer can be found in this plot. The number is 10 to the 10. Okay. So again, n sub I is 10 to the 10, the unit of number per cubic centimeter. So as I explained, for a given wafer, 12-inch wafer, uh, very tiny amount of volume, say 1 cubic centimeter, how many electrons are available in this intrinsic pure silicon material? You can answer that 10 to the 10 per cubic centimeter. 10 to the 10 electrons are available. Okay, so here in this two-dimensional bonding model, single free electron has been drawn and illustrated, and single hole is illustrated in this two-dimensional bonding model. However, this EHP, the total number of EHP is up to 10 to the 10, okay, per cubic centimeter. Okay, and here again, N indicates electron concentration. I guess there we go. N indicates that the number of electrons per cubic centimeter, and n sub I indicates the intrinsic carrier concentration. So in other words, the number of electrons in intrinsic or pure silicon material. Okay, so here n sub I is up to 10 to the 10. That is indicates the number of electrons per cubic centimeter. And again, because electrons and holes are created in pairs, right? So the whole concentration should be equal to the electron concentration. And that is equal to the 10 to the 10 because it is the pure semiconductor material. So in this plot, if you take a look at how many here, how many uh, conduction electrons are available in pure silicon, it turns out that 10 to the 10 conduction electrons available per cubic centimeter. Okay, so in pure semiconductor material, that is without any dopant atoms, without any impurity, without any non-silicon atom, N is equal to P is equal to N sub I. N is P is equal to Ni. For silicon case, and 10 to the 10. So we can derive this equation. N times P is equal to Ni times Ni, and 10 times 10 to the 10, you're gonna end up with 10 to the 20. So NP product is always 10 to the 20. So remember this equation. And this equation is named as mass action load. Mass action load. Okay. So mass action load NP product is identical to 10 to the 20. Let's go back to this slide again. So at room temperature, a certain amount of electrons which has originally participated in building up the covalent bonding in silicon crystalline material can be released out or becomes a conduction electrons so that a hole is created in pairs, which is denoted as EHP electron hole pairs. Okay? And even the total number of free electrons, conduction electrons in pure silicon, okay, intrinsic silicon crystalline material, that is 10 to the 10 per cubic centimeter. In other words, the number of holes created together with the free electron is also 10 to the 10 per cubic centimeter. Okay, all right. Now, before wrapping up this movie clip, let's take a look at the question. What is a hole? Now you can guess the hole is vacancy, kind of vacancy in a crystalline silicon material. However, once a electron is freed out, electron becomes conduction electron, then hole is always created together. So here, one thing that you should still puzzle, one thing, one point that uh, how come the hole is positively charged one? Uh, to understand why it is positively charged particle. Let's go back to the 2D bonding model again here. Uh, Now electron has been created here. And maybe this electron would like to sit down in this vacant site. Then this site will become whole. And now this electron would like to take this whole site. Then this hole created here. Can you see how the hole is moving? Now the very first electron is created, and second one, third one. And the hole is one, two, third. First, second, third, the holes are created in this sequence. So the electron is now moving from there to here in this direction, but the hole is created in this direction. Can you see the opposite direction? Okay, great. So now you can say that the electron is definitely negatively charged. The hole is now moving in the opposite direction of electrons, which is negatively charged ones. So that we can make a conclusion that the holes are positively charged instead of negatively charged. So here, what is a hole? Hole is movable, so mobile, and it is positively charged particle. And it is always associated, always related to the half-filled covalent bonding. So here, half-filled covalent bonding means this guy, right? Only half of it has been filled with electron. The other half is empty. Okay? So once half-filled covalent bond is found, there is always hole. Okay, so now the hole can be treated as positive charged mobile particle in the semiconductor material. Okay? Fluid analysis, so we will get back to this point later on. Okay, just at this point, what is a hole? you can answer that hole is a mobile, hole is positively charged instead of negatively charged because in a in a two-dimensional bonding diagram, once electrons which is originally participated in covalent bonding is freed out or becomes a conduction electron, there is uh, the hole has been left over. And once the other electron has tried to fill out that empty space, then the hole is now moved to the second conduction electron. So this mechanism, this process can easily have you understand how the hole is created and how the hole is moving around, roaming around in a crystalline silicon material, diamond structures. All right, that's all. So now let's stop here and see you in the next movie clip. So please try to read out the chapter 2 as much as possible and think how the electrons and holes are created in a crystalline silicon material. Okay? Then uh, try to follow up the next movie clip. Otherwise, this lecture note would be the very first obstacle, first barrier for students uh, to understand the introduction of solid state physics. Okay, so in the next movie clip, I'm going to tell you some details how the energy band diagram, energy level, energy band diagrams are created, okay, and its application as well. Okay, see you soon.